Hey everyone, welcome to part C of Unit 6, Thermochemistry. Today, we've talked a lot about enthalpy, and we're going to talk about the rest of energy today. We're going to talk about entropy and Gibbs free energy. And all of that kind of goes along whether something is spontaneous or not. So a spontaneous process is a process that can proceed without any intervention. Another way of saying spontaneous is thermodynamically favored. So if you hear thermodynamically favored, it just means spontaneous. Okay, so for example, if I twist this valve and make it horizontal, this gas will spontaneously flow over here. Okay, but they will not spontaneously put themselves back like this, where all the gas is inside B and none is inside A. So the gas in vessel V will spontaneously effuse into vessel A, but once the gas is in both vessels, it will not spontaneously return. So that's what I mean by spontaneous. Okay, also, if I leave a nail outside, it's going to rust. That is a spontaneous process. But if I leave a rusted nail outside, it's not going to magically unrust. That would be non-spontaneous. So processes that are spontaneous in one direction are non-spontaneous in the reverse direction. And all of our reactions are considered spontaneous in one direction, non-spontaneous in another. Processes that are spontaneous at one temperature could be non-spontaneous at another temperature. For example, ice will melt spontaneously above 0 degrees, but ice will not melt spontaneously below 0 degrees, or the other way. Water will freeze spontaneously at 0 degrees and below, but water will not freeze spontaneously above 0 degrees. So temperature plays a factor. So let's see. Above 0 degrees, it's spontaneous for ice to melt. Below 0 degrees, the reverse process is spontaneous. In a reversible process, the system changes in a way that the system and surroundings can be put back in their original states by exactly reversing the process. Nothing is reversible in terms of the chemistry definition. Okay, we can put things back, but not the way that they came to be. So for example, looking at these vessels, we can open this valve and spontaneously the gas will flow. I can get it back to looking like this, empty, and B is filled, but not by just moving the valve. So yes, I can reverse the process, but it's not reversible because I don't reverse it in the exact same way I did it. Okay, I did it by opening the valve. I can't reverse it by opening the valve. So that's what reversible means. And for our sake, nothing is reversible. Okay, so another one, we have a gas and a vacuum. If I flip this little divider up, the gas will spontaneously move and fill all of the space. Okay, but it's not reversible because I can't just flip this divider down and go back to this original position. Okay, I can get it back to this, but not by flipping the divider down. I would have to do some work and then flip the divider down. Okay, so nothing is reversible. Irreversible processes cannot be undone exactly by reversing the change, but doesn't mean they can't be undone at all. So spontaneous processes are irreversible. Everything we do is considered irreversible in this class. So that's a little bit about spontaneity. Entropy, which is capital S, can be thought of as a measure of randomness or disorder. So we talked about entropy a little bit when we talked about solutions. It's related. There's many things that factor into entropy. When it all really boils down to the molecule and the motion in the molecule. So just like energy and enthalpy, entropy is a state function, meaning you can do final minus initial. So you will have to do this on your homework. I'll give you the entropies of the products and the reactants. It's just products minus reactants, and you have to consider their coefficients. Okay, so we did the first law of thermodynamics. That's the law of conservation of energy. The energy of the universe is constant. The second law of thermodynamics states that the entropy of the universe increases for spontaneous processes. The entropy of the universe does not change for reversible processes. Remember, there's no such thing as a reversible process. So anytime something spontaneous happens, entropy increases. Okay, so in other words, for a reversible process, which there is none, the change in entropy for the universe is 0. For an irreversible or a spontaneous process, the change in entropy of the universe is greater than 0. This means that as a result of all spontaneous processes, the entropy of the universe increases. Okay, so entropy on a molecular scale. We don't tend to think about it like this too much, but this is really where it's coming from. Molecules exhibit many types of motion. So translational is moving from one place to another. So solids really don't have translational motion. Liquids move from side to side or whatever. And gases, they move all around. Vibrational motion, this would be their bonds vibrating. Now they can vibrate out, they can vibrate in, and they can vibrate side to side. So I know you can't see my full arm motions, but you can look at this. They can go out, they can go in, and they can go side to side. And they also have rotational movement. They can rotate about sigma bonds. So a guy named Ludwig-Boltzmann envisioned the motions of a sample of molecules at an instant in time, like taking a snapshot of all the molecules. He referred to each snapshot as a microstate. And the more microstates something had, the more entropy something had. Now, we're not actually going to look at microstates, but you're going to have to compare entropy of different molecules or different states of matter or stuff like that. So the number of microstates, and therefore the entropy, tends to increase with temperature because you have more motion, volume because you have more space for movement, and number of molecules. Okay. Entropy increases with freedom of motion. So therefore gases have a higher entropy than liquids, which have a higher entropy than solids. Solutions, generally when the solute dissolves, entropy increases. You're going from a solid and a liquid to more randomness, more disorder. Entropy increases when gases are formed from solids and liquids. Liquids or solution are formed from solids. The number of gas molecules increase. Okay, so you tend to be looking at the number of gas molecules by the coefficients, or the number of moles just of liquid or gas increase. So looking at this example, we have 2NO plus O2 yields 2NO2. In this reaction, would you say entropy increased or decreased? Entropy actually decreased because we had 3 moles of gas, 2 and 1, and we made 2 moles of gas. We're going to have less randomness or less disorder. So entropy decreased here. So that's a little bit about entropy. We'll bring back entropy and enthalpy together in just a second. The third law of thermodynamics states that the entropy of a pure crystalline substance at absolute 0 is 0. So molecules at absolute 0 have no motion, therefore they have no entropy. We have not reached absolute 0 in our universe yet, so this is just kind of a hypothetical thing, but it's saying absolute 0 means 0 motion. So there are standard molar entropies, just like there's heat of formation. The standard entropies increase with molar mass. Standard entropy is an extensive property, so it does depend on the number of moles. Okay, with a larger molar mass, the more protons, neutrons, and electrons, the more movement, the more entropy. Also, larger, more complex molecules have greater entropy because they're able to have more microstates. They have more motion.
So propane here would have the highest entropy value because it's got the most mass and it's the most complex of these 3 molecules here. So hopefully through this video, you learned what it means for something to be spontaneous or thermodynamically favorable, how temperature can affect spontaneity, what a reversible and irreversible reaction is, about entropy and how to make predictions about entropy, and the second and third law of thermodynamics. In the next section of the notes, we will learn about another energy value called free energy, and we will learn about the mathematical relationship between free energy, entropy, enthalpy, and temperature. Bye guys, I'll see you later.